let's say we have a aqueous solution that contains 1.25 milligrams of mercury and in 2.5 milliliters, or excuse me, 2.5 liters of aqueous solution. Let's calculate the concentration in molarity and parts per million. Now molarity, we know this quite well. We know molarity is going to be moles of mercury over liters. Okay, so we already know the volume of our solution in liters, so we just have to calculate the number of moles of mercury. So we know how to do that. 1.25 milligrams of mercury. We're going to need to convert to grams so that we can use the molar mass, and there's 1,000 milligrams and 1 gram. And then if we look at our periodic table, we'll see that in 1 mole of mercury we have 200.59 grams of mercury. Grams of mercury cancel out, milligrams cancel out, and we're left with 6.23 times 10 to the negative 6 moles. Okay, we can plug that into our calculation, and that would be 6.23 times 10 to the negative 6 moles of mercury divided by 1 liter, and, or excuse me, 2.50 liters. Again, that was our volume of our solution, and that will give us a value of 2.49 times 10 to the negative 6 molarity. Now, as you can see, that is a very small number. Okay, it might be more convenient, especially if this we're just talking, not referring to a stoichiometric application. It might be more favorable to use something like parts per million or parts per billion. So remember, parts per million, just like percent, parts by, or excuse me, just like percent, is the fraction of the mass of your solute over the mass of your solution times your multiplication factor, and in this case it would be a million rather than 100. So mass of mercury over mass of solution. We have our mass of mercury, and this would be, of course, multiplied by a million. For 10 to the 6th. So we've got our mass of mercury. Now we need to know the mass of our solution. Okay, so we've got it in volume. Okay, so we just convert liters to milligrams so that we keep them in the same solution, same units, and we can do that. 2.50 liters. Okay. Turns out, since this is such a dilute concentration, we can probably just assume the density of water, so we're going to have to convert this to milliliters, 1 liter, and the density of water is 1.00 grams per milliliter, and again, because this concentration is so dilute, that's a pretty good approximation. And then in 1 gram, we've got 10 to the 3rd milligrams. Grams cancel out, milliliters cancel out, liters cancel out, and so that way we have both our mass of mercury and mass of solution in milligrams. This is going to give us a value of 2.50 times 10 to the 6th milligrams. And so what we're going to do is 1.25 milligrams of mercury divided by 2.50 times 10 to the 6th milligrams of solution times 10 to the 6th for our multiplication factor. This is going to give us a value of 0.50 parts per million. At some point in time, or in various situations, that might be much more convenient to use parts per million rather than molarity. Okay, so just like percentage and just like molarity, we can use concentrations such as parts per million or parts per billion as a conversion factor. Okay, so anytime you see parts per billion, notice that means that this is 45 parts, and so since this is by mass, you can use any units of mass here. Let's say 45 grams of lead per billion grams of solution. Okay, so if you've got a 1.75 liter bottle of water, your solution, we can figure out how many grams of lead we have in there, and then of course if we want to calculate it in moles, we can do so as well. So let's start off with 1.75 liters. Okay, just like before, we're going to convert these to milliliters so that we can use the density of water to convert to grams. Okay, and in 1 liter, there's 1,000 milliliters. Again, this is such a dilute solution, we can assume the density of water is 1.00 grams per milliliter. Milliliters cancel out, liters cancel out. And here we're going to use our conversion factor. If we had 1 billion grams of solution, we'd have 45 grams of lead. And of course we can go to our periodic table and we can find that in 1 mole of lead we've got 207.2 grams of lead, and this is going to give us an answer of, if everything cancels out, those are on our calculator, 3.8 times 10 to the negative 7th moles of lead. Okay, so let's use parts per million as another conversion factor. Figure out how many moles of CO2 are in 2.0 liters of air. Okay, if we know the concentration of carbon dioxide in now a gaseous solution, 360 parts per million by mass, and the density of air, we can calculate the number of moles of CO2 in 2.0 liters of air. Okay, so again, 360 parts per million, that can be equal to 360 grams of CO2 divided by 10 to the 6th parts per million. Okay, just using it as a, no, that's not parts per million, per grams of our air. Using that concentration term as a conversion factor. Okay, so what are we going to do? We're going to convert 2.0 liters of air into moles of CO2 using parts per million as a conversion factor. I imagine we're going to need to convert from volume, liters, into some form of mass, and we can do so with kilograms. Okay, so starting off, 2.0 liters of air. Okay, we're going to need to go to meters cubed. So one way we can do that is by first converting liters into milliliters. Milliliters, the definition of a milliliter is 1 centimeter cubed. And if you look back, or we can even calculate the conversion factor for centimeters cubed to meters cubed, I know that there are 10 to the 2nd centimeters in 1 meter. And if I want to do the cubic conversion factor, I'm just going to cube both sides. So that multiplies the exponent, so this is going to be equal to 1 meter cubed. There are 10 to the 6th centimeters cubed. Okay, and now I can finally use my density as a conversion factor, in that I've got 1.1839 kilograms of air per meter cubed. And then I'm going to start to use this as a conversion factor. So first I'm going to go from kilograms, 1 kilogram, 10 to the 3rd grams. I'll also continue this conversion factors down here. And then finally I've got my 10 to the 6th grams of air and 360 grams of CO2. And then if we calculate the molar mass of CO2, we got around 12 for carbon, 16 for the 2 oxygens, so that's 32, so that's going to be around 44.0 grams of CO2 per 1 mole. And that will give us an answer of 1.9 times 10 to the negative 5th moles of CO2 and 2 liters of air.